In this video lesson, we want to look at some examples for how one can calculate and use specific heat data and also get a better sense of order of magnitude of the types of errors that one will encounter with some of our estimate techniques. So in this first example, we're going to look at HCl as a gas. At 1500 Kelvin, C sub P is equal to 34.06 joules per mole Kelvin. In this case, we just simply want to compare this to what if I assumed this was an ideal gas. So HCl, or anything with only two molecules, is going to be an H connected to a Cl, and so they have to form a line. So two molecules always will be linear. And so therefore, C sub P is approximately 3.5 R. Now in this case we have C sub P in joules per mole Kelvin, so to minimize my work I'm going to choose R as 8.314 joules per mole Kelvin. So 3.5 times 8.314 joules per mole Kelvin is 29.1 joules per mole Kelvin. So what's the error on this one? Well, take the 34.06, subtract off our estimate, divide by the correct value, times 100%, and this is really very close to 15% error. Okay, so you're better than a wild guess, but 15% error is fairly significant. In this example, we want to look at delta H for liquid benzene varying from 20 degrees C in 1 atmosphere to 50 degrees C in 3 atmospheres. Now we're going to need data for liquid benzene, so if you go to the appendix of the textbook, we find that the density is going to be 0.879 grams per milliliter. The molecular mass or molecular weight is 78.11 grams per mole, and C sub P for T in degrees C is 126.5 times 10 to the minus third plus 23.4 times 10 to the minus 5 T. Remember, we're multiplying by 10 to the negative fifth, solving for A, solving for B. And this is going to have units of kilojoules per mole Kelvin for temperature in degrees C. The other thing that we want to do is we want to have a calculation process path. So if I'm starting at 20 degrees C, 1 atmosphere, and somehow getting to 50 degrees C, 3 atmospheres, it's going to be much easier if I look at just taking these in two various steps and say 20 degrees C, 3 atmospheres, so I'll hold the temperature constant, change the pressure, and then hold the pressure constant and change the temperature. So this is one of many process paths that are possible. I'm going to calculate this as delta H1 and this one as delta H2. Delta H1, if there is no temperature change, is going to be V delta P. Now the reason I chose this as the path is because the density value that I have is for at room temperature. So it's going to be very close to 20 degrees C. And so therefore I have appropriate data. So 78.11 gram per mole divided by 0.879 grams per milliliter will give me units of milliliter per mole. And then I'm going to multiply times the pressure change. In this case, 3 atmospheres minus 1 atmosphere. Final minus initial. Next, I need to work on my units. 1 liter is 1,000 milliliters. And using values of R as ratios, 8.314 joules per mole Kelvin is equivalent to 0.08206 liter atmosphere per mole Kelvin. Moles Kelvin cancel, liters cancel, atmospheres cancel. Okay, so, and this milliliter cancels with that. So I'm going to be left with delta H1 is 18.01 joules per mole. Next, let's calculate delta H2. Now, delta H2 is where I hold the pressure constant and change the temperature. So I'm going to integrate from 20 to 50 degrees C, C sub P dt. C sub P is given up above. So this is going to be 126.5 times 10 to the minus 3t plus 1/2 times 23.4 times 10 to the minus 5t squared, evaluated from 20 to 50. I'm using degrees C because that was stated in the data table. If you plug these numbers in, I'm going to get delta H2 with units. It's going to be 4.04. C sub P was kilojoules per mole Kelvin times units of the dt, which is Kelvin. So 4.04 is kilojoules per mole. If I want to get it into joules per mole to match the other, 4,000, or no. Multiplied by 1,000, 4040.7 kilojoules per mole. And so delta H is simply the sum of these. Okay, and so 4058.7 joules per mole, or with more appropriately sig figs, 4060 joules per mole. Notice that a very small contribution comes from the pressure change. Most of the contribution is due to the temperature change. Now in this last example, we're going to look for the change in enthalpy for liquid benzene as it varies from 20 degrees C, 1 atmosphere, to 50 degrees C, 3 atmospheres. But this time we're going to use Kopp's rule and assume that we don't have C sub P data. So the data for Kopp's rule is shown here. We're talking about liquid benzene. We have 6 carbons and 6 hydrogens. And so C sub P is going to be approximately 6 times 12 plus 6 times 18, which is 180 joules per mole degrees C. Now in this case, I can only use this for calculating the delta T portion. So this is the delta H2. For delta H1, I'd still use the V delta P that I had before. So delta H2 is going to be equal to C sub P delta T if C sub P is constant. So in this case, it's 180 joules per mole degrees C times 30 degrees C is the delta T. And so delta H is going to be 5,400 joules per mole. If I add that to delta H1, then I would get 5,420 joules per mole. Now in this case, the percent error is 34%. Kopp's rule is truly a desperation effort, okay? It's not ever going to be very good, but it's better than just a wild guess. You are at least within, an order of magnitude of the actual answer. So this concludes our lessons on specific heats. In the next set of lessons, we're going to talk about latent heats and how those can also be used to calculate our hypothetical process path energy changes.